As we're in 3.2, let's work through some examples. So one of the first things that was discussed in 3.2 was whether events are independent or dependent. So let's look at number 10. A father having hazel eyes and a daughter having hazel eyes, are they independent or dependent? Well, we know through science that there is a connection between attributes of children and parents. Children tend to look like their parents. So the eye color of the father or mother does impact what eye color the child might have, so those events are dependent. One event is connected to the other. Number 12, not putting money in a parking meter and getting a parking ticket. If I don't put money in a parking meter, I am more likely to get a parking ticket than if I do put money. So there is a connection here. If I do this, if I don't put money in there, I might get a parking ticket. If I do put money in the meter, then I probably won't get a parking ticket. So one event affecting the other one, they are dependent. How about a ball is selected from a bin of balls numbered 1 through 52? That ball is put back and then we select another number. The key here is replacement. If you put the ball back in, then you're drawing from the same group of numbers each time. So one selection is not affecting the other. So those two events are independent. Now, what would one that would be dependent look like? If I take a ball out of a bucket and I don't put it back, then when I draw the second ball, then there are fewer to choose from. So what happens on the first event has affected what's going to happen the second time. So in that case, those would be dependent. All right, so that's independent and dependent. Let's look at an example. Let's look at number 20 as an example of the multiplication rule. So a coin is tossed and a die is rolled. Find the probability of tossing a tail and then rolling a number greater than 2. So the probability of tossing a tail and rolling a number greater than 2. Now if I toss a coin and I roll a die, those two have no impact on each other. The outcome of the coin toss is not impacted by what happens when I roll that die and vice versa. So these are independent events. And our multiplication rule for events that are independent say that we take the probability of the first event times the probability of the second event, multiply those together, and that gives us the probability of both occurring. So if I toss a coin, there are two sides, and out of those two sides there's one tail, so the probability of tossing tails is 1/2, 1 out of 2. If I roll a die, it has 6 sides. And how many numbers on a die are bigger than 2? So there's a 3, 4, 5, and 6. So 4 of the numbers on a die are bigger than 2. So if I multiply this together, 1 times 4 over 2 times 6, which reduces 4 as a decimal, 0.33, repeating. So that's the likelihood of tossing a coin and getting a tail, and rolling a die and getting a number greater than 2. Of course, we could check that by making a tree diagram, but you can probably see quickly that if our sample space gets excessively large, the tree diagram is going to get really messy. So if we can use our multiplication rule to get our probability, probably going to be quite faster. All right, let's look at another example. Number 22 says, in a survey, 510 U.S. adults were asked whether they drive a pickup truck and whether they drive a Ford. So 2 questions. Do you drive a truck and do you drive a Ford? The results showed that 3 in 10 adults surveyed drive a Ford. So the probability of a person driving a Ford was 3 out of 10. Out of every 10 people, 3 drove a Ford. Of the adults surveyed that drive Fords, 2 in 9 drive a pickup truck. So let's think about what that says. They drive a Ford, so that's a condition. Given that they drive a Ford, how likely is it that they drove a pickup? So out of the people that drove a Ford, the people that drove a pickup, that was 2 out of 9. So then the question is, find the probability that a randomly selected adult drives a Ford and drives a pickup. So we're looking for the probability that the person drives a Ford and they drive a pickup. Now notice this is a conditional statement. The likelihood of driving a pickup knowing that they're a Ford owner. So if we have a conditional probability and we're wanting to find an and statement, that's the probability of one event times the conditional probability of the other event. If we know one probability and the other probability based on the original one, then that is our general multiplication rule. So these are not independent, these are dependent, so we have to use our general rule. One thing we'll always notice is whatever the condition is here, that's the standalone probability here. So the probability of driving a Ford is 3 out of 10. The probability of driving a pickup, now that we know they drive a Ford, is 2 out of 9. So if we multiply that together, 3 times 2 over 10 times 9. And then if we just want to convert that to a decimal, 6 divided by 90, 0.6 repeating. I think I said that wrong. 0.06 repeating. All right, let's look at number 28. Number 28 says the probability that a Caucasian person in the United States has type AB blood is 1%. So the probability that a person has type AB blood is 1%, or as a decimal, 0.01. 4 unrelated people in the United States are selected at random. So since they're unrelated and we're selecting them at random, these are independent. What we find out about one person does not impact what we know about another person. So then we have several questions. The first question, find the probability that all 4 have type AB blood. So that's the probability that person 1 has AB blood. Let's say the AB sub 1. So the first person has AB blood, and the second person has AB blood, and the third person has AB blood, and the fourth person has AB blood. Now, since these are independent, we can use our special multiplication rule that says we take each of their probabilities and multiply them together. We don't have to use a condition in this one because they are independent. So the probability that the first person has AB blood is 0.01. The same probability for the second person to have AB blood, and the third, and the fourth. So if we multiply those together, or we could do 0.01 to the 4th power, we get 0.00000001 1. So not very likely. Very unlikely that if you select 4 people that they all have type AB blood. So then let's look at the next part. Find the probability that none of the 4 types have AB blood. So if the likelihood that they do have AB blood is 0.01, then the probability that they do not have AB blood is just a complement. So 1 minus that probability. So the likelihood that they do not have AB blood, 99%, 0.99. So the probability that the first person does not have AB blood and the second person does not have AB blood and the third person does not have AB blood and the fourth person does not have AB blood. So these are also independent. What type of blood one person has, if they're not related, is not impacted by another person. So since these are independent, we just multiply each of these probabilities together. So each of these have a probability of 0.99. 0.99 times 0.99 times 0.99 times 0.99. We could just call that 0.99 to the fourth. And we get that to be about 0.96. Or about 96%. So it's way more likely that you select 4 people that don't have type AB blood than you do selecting 4 people that do all have type AB blood. So now let's look at part C. Part C says, find the probability that at least one of the 4 has type AB blood. Now notice the connection between B and C. B and C is none, so that's nobody. Not a single person has AB. But C is at least one. So these are actually complements. Either no one has that blood type or at least one person does. If at least one person does, then that's not in the group none. If nobody has type AB blood, then it's not true that at least one person does. So if we want to know the probability that at least one person has type AB blood, then that's going to be 1 minus the probability that no one had type AB blood. Well, we just found out that the probability that no one in our group had type AB blood is 0.96. So if we subtract those, there is a 4% chance that at least one person in the group has that particular blood type. So one of the points of doing this particular question is noticing the correlation between at least one and none. At least one and none. Those are complements of each other. So if we know one of those probabilities, we can get the other one by just doing 1 minus that. One other thing I want to mention, just in case, the example we found, we were looking for an and statement, either a conditional probability or one that was independent using that and statement. Occasionally, we're looking for the conditional probability. Now, the book is going to give you a special formula to do this, but let's look at where it comes from. If we want to find the probability of one event and the other event, it's the probability of one event times the conditional probability of the other event. And remember, we mentioned that whatever event stands by itself here, the other probability is based on that condition. So sometimes a book will write it this way as well. But A and B are just random names for events. So this is the standalone event. So the other probability is based on that condition. So depending on what you're given, we might be told the probability of A and B, and we might be told the probability of one of the events. If we know those two pieces of information, we can find the other one. How would we get this by itself? Well, the opposite of multiplying is to divide. So if we divide both sides by A, then the book is going to tell us that the probability of one event given the other one is the probability of both events divided by the probability of one of those events. And that is perfectly okay that you write that formula down. To me, the fewer formulas I have, the better. I'm less likely to mix things up. So I generally use just one of those. I'll just take this formula and I plug in for whatever pieces of information I know. If I know a conditional probability and the combined probability, then I'll solve for this quantity. If I know this one and this one, then I'll solve for that one. Or in most examples we've known one event and the conditional probability of the other event, and we can use that to find this one. Similarly, if our events are independent, if one does not affect the other one, then the second probability is not conditional, it's just on its own. So whichever two pieces of information I'm given, I plug those in and I solve for the other one. We should know how to isolate our unknown. So plug in, get all of the things that we know on one side, and we'll be left with what we don't know.